So today we're going to be talking about ocean depths and pressure. So today we're going to be talking about ocean depths and pressure. In 2012, James Cameron, who directed the film Titanic, made headlines when he traveled to the Challenger Deep. This is the deepest known point on the ocean floor, almost 11,000 meters below the surface. Cameron was the first person to travel there alone. He made the trip in a deep-sea diving vehicle named Deep Sea Challenger. The vehicle that was pictured is another deep-sea diving vehicle named Alvin. Alvin is no longer used for seafloor exploration, but by the time it had retired, In 2012, James Cameron, who directed the film Titanic, made headlines when he traveled to the Challenger Deep. This is the deepest known point on the ocean floor, almost 11,000 meters below the surface. Cameron was the first person to travel there alone. He made the trip in a deep-sea diving vehicle named Deep Sea Challenger. So what is pressure anyway? Well, it's a really good question. Pressure can be thought of in a lot of different ways, but in its simplest form, pressure is given by the equation pressure equals force divided by area. When we're talking about a gas or a fluid like water, we can think of the force part of the equation as the weight of the column of the fluid pressure down on a point at a given size. Hence, the unit of pressure, pounds per square inch. It is nicely demonstrated by the simple experiment of filling a tube of water and punching holes at different heights. Notice that the jet at the bottom of the column travels furthest because the pressure is acting on it. And this is caused by the weight of the water pressing down, and it's at its highest point at that. When we talk about pressure in the ocean, we are referring to hydrostatic pressure, which is the result of the weight of the water column pressing down on an object due to gravity. The deeper you go, the more water is above you, and the greater the weight, and thus the pressure of that water. At the surface, we experience 1 atmosphere of pressure due to the weight of the atmosphere above us. So imagine stacking a group of books. Each weighs about 2 pounds. When there's only 3 books, the table has 6 pounds pushing onto it. When there are 6 books, there are 18 pounds on the table. Stop. Imagine stacking a group of books. Each weighs about 2 pounds. When there are only 3 books, the table has 6 pounds pushing onto it. When there are 6 books, there are 12 pounds pushing on the table. When there are 9 books, there are 18 pounds of pressure. This is the same way that the ocean works. As you go deeper and deeper into the ocean, there is more water pushing down. This leads to a very high pressure in the deeper parts of the ocean. If you consider that the average depth of the ocean is about 3,800 meters, the pressure at that depth would be 381 times greater than the pressure at the surface. There are several important consequences of high pressure at depth. First, due to Boyle's law, which states that the volume of a gas is inversely related to pressure, High pressure will act to compress air spaces, such as the lungs of a diving animal or a person, or the space inside of a submarine. Submarines and submersibles must therefore have very strong hulls to reduce this compression at extreme depths. When a scuba diver dives, the tank that supplies oxygen gives it at the same pressure as the surrounding pressure. The most important rule of scuba diving is not to hold your breath. Why? Well, the pressure on us while we're diving causes the cavities in our body that contain air to be compressed. If we hold our breaths and expand our lungs but do not breathe out, the pressure can cause damage to our lungs and can burst our lung sacs. When a diver ascends to the surface, the pressure is decreased, which causes the volume of the gas in our cavities to expand. That is why divers ascend in increments to lessen the risk of over and over expanding the lungs. On the left, a breath-hold diver's lungs on descent will compress and then expand again on ascent. On the right, a scuba diver breathes more air on descent to keep the lungs full, but must exhale on ascent to let the expanding gas escape. Go back to expanding the lungs. On the left, a breath-held diver's lungs on descent will compress and then expand again on ascent. On the right, a scuba diver breathes more air on descent to keep the lungs full, but must exhale on ascent to let the expanding gas escape. Second, Henry's law states that at higher pressure, a fluid will contain more dissolved gas. This means that deeper, higher pressure water may contain more dissolved gases than surface water. This also has implications for human divers. According to Henry's law, if you increase pressure, you increase the amount of gas that can dissolve in a fluid, such as blood. Conversely, when you reduce pressure, the fluid holds less dissolved gas, and the excess gas will leave the solution, often in the form of bubbles. This means that as a diver descends, gases dissolve more easily into our body than at normal atmospheric pressure. Nitrogen is a gas that can be found in normal breathing air. When a diver descends, nitrogen dissolves into our body more easily. So if a diver ascends too fast, not only will he strain the lungs due to Boyle's law, also nitrogen bubbles may form, which causes the bends, or decompression sickness. The bends occurs when the pressure is released too fast on ascension and the nitrogen gas bubbles escape. As you descend down into the ocean, pressure increases linearly with depth. There is an increase of a pressure of 1 atm or atmosphere for every 10 meters increase in depth. So at 1,000 meters depth, the pressure would be 101 atmospheres. 100 atmospheres of pressure due to the depth, plus the 1 atmosphere that was present on the surface anyway. This leads to a very high pressure in the deeper parts of the ocean. If you consider that the average depth of the ocean is 380 meters, the pressure at that depth would be 381 times greater than the pressure at the surface. The equation for this is depth in meters divided by 10 plus 1. Notice that the graph has a negative slope. However, it does indicate that as you increase in depth, you increase in temperature. This is a positive correlation. Water is very effective at absorbing incoming light, so the amount of light penetrating the ocean declines rapidly. It's attenuated with depth. At 1 meter depth, only 45% of the solar energy that falls on the ocean surface remains. At 10 meters depth, only 16% of the light is still present, and only 1% of the original light is present at 100 meters. No light penetrates beyond 1,000 meters. Plants use sunlight as their primary source of energy through a process called photosynthesis. Photosynthetic organisms in the ocean, such as algae and phytoplankton, must live in well-lit surface waters called the euphotic zone. The euphotic zone is the upper part of the ocean that receives bright and clear sunlight. In clear tropical waters, the euphotic zone may extend to a depth of about 80 meters. Sunlight does not penetrate as deeply near the poles. So in these areas, the euphotic zone may be less than 10 meters deep. Turbid, muddy waters may have a euphotic zone of only a few centimeters in depth. The dysphotic zone is the water layer beneath the euphotic zone. In clear water, it may extend as deep as 800 meters. The dim blue light that penetrates this zone is not sufficient to sustain photosynthesis. The photic zone is made up of the euphotic zone and the dysphotic zone. The aphotic zone is the water layer where there is no visible sunlight. Most of the water in the ocean lies in the aphotic zone. Some lakes are also deep enough to have an aphotic zone. When sunlight strikes the ocean, some of it reflects off the surface back into the atmosphere. The amount of energy that penetrates the surface of water depends on the angle at which the sunlight strikes the ocean. Near the equator, the sun's rays strike the ocean almost perpendicular to the ocean's surface. Near the poles, the sun's rays strike at an angle rather than directly. The direct angle of the sun's rays to the surface of the water at the equator means that more energy penetrates the surface of the water at the equator than at the poles. Water absorbs almost all of the infrared energy from sunlight within 10 centimeters of the surface. In this very shallow layer, light energy is converted to heat, which can raise the water temperature and cause some of the water to evaporate. When winds and waves stir the surface of the ocean, heat mixes into cooler water layers below. 90% of the sun's radiant energy is absorbed by ocean waters. This heats up the ocean. Dark blue ocean water reflects less than 10% of incoming sunlight. The wavelengths at extreme ends of the visible spectrum are attenuated faster than those wavelengths in the middle. Longer wavelengths are absorbed first. Red is absorbed in the upper 10 meters, orange by about 40 meters, and yellow disappears before 100 meters. Shorter wavelengths penetrate further, with blue and green light reaching the deepest depths. This explains why everything appears blue underwater. The colors that we perceive depends on the wavelengths of light that are received by our eyes. If an object appears red to us, that's because the object reflects red light but absorbs all of the other colors. So only the color reaching our eyes is red. Underwater, blue is the only color of light still available at depth. So it's the only color that can be reflected back to our eyes. And everything has a blue tinge underwater.